Hello and welcome to the ElectroMaster channel. In today's episode, we have on the workbench a VACON 0100 inverter, which came to me with a serious issue. Water accidentally got inside, and after that, it stopped working. I'll take the inverter apart, we'll analyze together what happened inside, repair it, and then reassemble it to see if we can bring it back to life. Stay tuned until the end to see all the steps. As you can see, I've already started disassembling the inverter. I will completely take it apart piece by piece to carefully inspect every component. This includes removing the casing, separating the power board, the control board, and checking all connectors, capacitors, and semiconductors for any signs of water damage or corrosion. By fully dismantling the unit, we'll be able to identify exactly which parts have been affected and determine the best way to bring the inverter back to proper working condition. As I can see, there are clear traces showing that water has penetrated the electronic board. Some areas are visibly affected with deposits, oxidation, and possible short circuits on the tracks and components. Under these conditions, the chances of bringing the inverter back to life are not very high, since water can cause both visible damage and internal deterioration of components. However, I will continue with the cleaning, inspection, and testing process, because sometimes, even in severe cases, certain circuits can still be restored. There are clear signs of water ingress even in the IGBT transistor bridge area. This is a serious issue since the IGBTs are critical components in the inverter's operation, responsible for switching high voltages and currents. The presence of water in the section can cause short circuits between terminals, internal insulation breakdown, and in some cases, permanent destruction of the transistors. Furthermore, the contacts and solder joints may suffer from corrosion, leading to loss of conductivity and unstable performance. The next step will be to check for potential short circuits in the transistor's diodes. This involves measurements using a multimeter or dedicated testing equipment to determine whether the internal diodes are still functional or have been damaged by water ingress. Based on the results of these tests, I will decide whether it's worth continuing the repair or if the inverter is too damaged to be recovered. This is a critical step as the IGBT diodes play a key role in current switching and circuit protection. After performing measurements directly on the IGBT module, I tested the internal diodes of the transistors. The result is positive. No short circuits were detected. This indicates that despite the water exposure, the internal structure of the transistors and the integrated diodes has not been compromised. The absence of short circuits is a good sign that the IGBT module is still functional and can remain in the circuit, giving me confidence to continue with the repair process. I will now proceed with cleaning the main electronic board, where clear signs of corrosion can be seen on the contacts linking the IGBT transistor bridge to the control board. The corrosion on these contacts can cause increased transition resistance, loss of conductivity, and even intermittent failures in the inverter's operation. The cleaning process will involve removing the oxidation deposits and restoring the contact surfaces to ensure a stable and reliable electrical connection between the modules. After a thorough cleaning and detailed inspection of the electronic board, I proceeded with reinstalling it into the inverter assembly. During the inspection, I did not find any shorted or burnt components, which is a positive sign regarding the board's integrity. The reassembly is performed carefully to ensure proper repositioning of all connectors and secure mechanical fastening of the main board, so that the contacts between the IGBT module and the electronic board remain stable and reliable. The control board and the display module show no visible signs of water ingress and therefore do not appear to have been affected. There are no traces of corrosion, deposits, or damage on the connectors and circuits. For this reason, I will not focus extensively on them, but I will perform a visual inspection and a few basic tests to confirm their functionality. It is worth noting that these modules are less exposed to high currents and generally have better tolerance to external factors compared to the power stage. For the initial test, I will power the inverter with 230 volts single phase instead of the normal 400 volts three-phase supply. The purpose of this test is not to check the full power stage operation, but only to verify the control board and the display module. This method allows me to confirm whether the control logic starts up, whether the display operates correctly, and if any error codes are generated. Using a limited supply reduces the risk of further damage and provides a safe way to perform a preliminary diagnosis. After powering the inverter, the fan starts up correctly and the display module is operational, responding properly to key presses. No major errors are present except for the "not ready" message, which is expected at this stage since the inverter is not connected to the actual load and is missing some required interface signals. Based on these results, I can conclude that the control and display sections are working properly, and therefore, the inverter will be sent for further testing directly on the machine under real operating conditions. As you will see, the inverter is now running on the machine within normal parameters with no major errors. The repair was successful and the equipment is ready for operation. That's it for today's episode here on ElectroMaster. If you enjoyed it and want to see more repairs and technical walkthroughs, don't forget to like and subscribe. I also invite you to become a channel member to support my work and get access to exclusive content. See you in the next video.